Hello, and welcome to the Engines and Power Plant lesson in the PMDG 737 Next Generation Groundwork from Angle of Attack. This lesson will cover the following topics: 737NG Engine System Overview, Engine Fuel System Overview, Engine Oil System, Starting and Ignition Procedures, and Thrust Reversers. We will not be discussing auto thrust in this lesson, as we have comprehensively explained it in the autoflight lesson. The 737NG is powered by two CFM56 Type 7B engines that provide power to propel the aircraft forward and also to power the following aircraft systems: electric, pneumatic, and hydraulic. The 737 hydraulic, air, and electric systems lessons include comprehensive discussion about the relationship between the engines and the respective aircraft system, so we won't be discussing those relationships here. To create the required forward-pushing force or thrust, each engine has the following main components: fan, booster or low-pressure compressor, high-pressure compressor, combustion chamber, high-pressure turbine, low-pressure turbine, and exhaust. The fan has 24 fan blades that spin together counterclockwise to increase the speed of the air entering into the engine. A splitter divides this air into two types: primary airflow and secondary airflow. The primary airflow, which is about 20% of the total air entering the engine, enters the engine core and goes through the rest of the components that we mentioned previously. The secondary airflow bypasses the engine assembly and is rushed out of the engine at a fast speed. The ratio between secondary and primary airflows is known as bypass ratio. The CFM56-7B is a high bypass ratio engine. The higher the bypass ratio, the better fuel efficiency is achieved and a lower engine noise is produced. The fan essentially works like a light aircraft propeller. However, it's designed to perform considerably better at higher altitudes and airspeeds. After passing through the fan, the high and low pressure compressors compress the air to increase its pressure and temperature. The low pressure compressor has 3 stages of compression, whereas the high pressure compressor has 9 stages. After the air has passed through all 12 stages, its temperature is roughly 450 degrees Celsius. Moving on, the combustion chamber takes this dense, compressed air from the compressors and also receives fuel from a series of fuel nozzles. These two elements are joined to create a fuel-air mixture that is burnt in order to make hot gases. At this point, the air-fuel mixture temperature will have increased to roughly 1700 degrees Celsius. Because the hot gases in the combustion chamber carry so much thermal energy, they move further to the high-pressure turbine. This is a single-stage turbine that converts some of that thermal energy into mechanical energy in order to move the high-pressure compressors. The high-pressure turbine is linked to the high-pressure compressors with a shaft. The high-pressure shaft also turns an accessory gearbox that holds and operates the airplane and engine accessories. Some of these are the hydraulic pumps, sensors, oil filters, etc. The remaining thermal energy from the hot gases is also converted into mechanical energy by the low-pressure turbine. This turbine has 4 stages and moves the low-pressure compressors, or booster, and also turns the engine fan. The fan, booster, and low-pressure turbine are linked with a shaft that is mechanically independent from the high-pressure shaft we mentioned earlier. A surrounding engine cowling protects all the engine components. This cowling has an aerodynamically smooth surface in order to minimize drag. Access doors are available in order to perform maintenance. In addition, in the event of a foreign object being ingested into the machine, this cowling works to contain engine components if there is a breakup. Flying engine parts don't bode well for anything on the aircraft, including passengers. To put things in simple terms, the secondary and primary bypass air work in conjunction to create thrust, or fast-moving air, that drives the aircraft forward. This works in a carefully synchronized mechanical harmony, considering fuel efficiency and low noise print along the way. Worth mentioning at this point, there are several controls and indications associated to the engine system on the 737NG. We'll be discussing these progressively throughout this lesson. However, the engine indicating system can be grouped into two categories: primary engine indications and secondary engine indications. The primary engine indications are those of immediate importance to the flight crew. They are low pressure shaft speed, or N1, exhaust gas temperature, or EGT, fuel flow, fuel quantity per tank, total air temperature, and active thrust mode. The secondary engine indications are not required to be constantly monitored. However, they're still significantly important. They are high pressure shaft speed, or N2, oil pressure, oil temperature, oil quantity, and engine vibration level. We don't expect you to know what these are right now, as we'll be teaching them throughout this lesson and continually as we fly the aircraft. Much of what happens with the engines can be categorized as seeing is believing, so that's exactly what we'll do throughout your training. Engines on the 737 ideally work with Jet A or Jet A1 fuel supplied from the wing tanks and center tank. This fuel is pressurized and is boosted into the engine system with booster fuel pumps. Immediately outboard of each engine strut, there are engine fuel spar valves. These fuel spar valves permit fuel flow from the engine feed system towards the engine fuel supply systems. There is one fuel spar valve on each wing. The fuel spar valves are controlled with the engine start levers located below the throttles on the control stand. There are two start levers, one for each engine. Start levers are used to start and shut down the related engine. Each start lever has the following positions. Cutoff. This closes the fuel spar shutoff valve, prevents fuel from flowing into the engine fuel supply systems, and also de-energizes the engine ignition system. The ignition system will be discussed further along in this lesson. Idle. This position electrically opens the fuel spar shutoff valve and also opens another engine-mounted fuel shutoff valve. When the start levers are placed in idle, the ignition system is also energized. Moving on, once the fuel is passed through the fuel spar shutoff valves and is free to flow into the engines, it passes through four important stages: fuel pump first stage, fuel oil heat exchanging, fuel filtering, fuel pump second stage. Both stages of the fuel pumps are used to increase the fuel's metered pressure in order to deliver a constant high-pressure flow into the engine fuel system. Following the fuel pumps, it's important to know about the fuel oil heat exchangers. In the 737NG, fuel may be as cold as negative 43 degrees Celsius. Naturally, it takes a lot of energy to bring its temperature up to the whopping 1700 degrees Celsius that is achieved during the engine combustion process. On the other hand, in order to lubricate moving parts, engines have oil. This oil gets very hot during operation and it must be cooled. The best solution to this problem is to exchange thermal energy between hot oil and cold fuel so that oil becomes colder and fuel becomes hotter. This occurs in two stages. First, the fuel passes through the Integrated Drive Generator, IDG, oil heat exchanger. And secondly, it passes through the main engine oil heat exchanger. The IDG will be explained in another lesson. At this point, just note that the fuel is super cold and needs to be warmed up. Now, time for filtering. Any form of fuel contamination is bad. It makes combustion difficult and subsequently decreases the engine life. In some cases, when the fuel is excessively contaminated, it may even lead to an immediate engine failure. To prevent this, fuel is filtered to minimize the presence of contaminants. If contamination clogs the filter, a bypass valve opens and fuel does not go through the filter before it continues towards the engine, ensuring that fuel flow is not sacrificed. It's better to have contaminated fuel temporarily than no fuel at all. Following all the components we've discussed, fuel finally goes through a hydromechanical unit. The HMU will not be covered in this lesson as it's discussed in the fuel system lesson. However, inside the HMU, fuel is metered and fuel flow is controlled by an electronic engine control, or EEC. The EEC uses analog and digital data to calculate the required engine fuel and controls output to operate the engine through the fuel supply that the HMU provides. The mass flow of fuel that goes from these components into the fuel nozzles in the engine is measured by a transmitter that provides fuel flow indication. Fuel flow and fuel used are displayed as secondary engine indications in the display units. There is a fuel flow switch in the center forward panel that has 3 positions. Reset shows fuel used, resets it to 0, and then displays fuel flow. Used shows fuel used since last reset and then displays fuel flow. Rate simply displays fuel flow to both engines. You may be wondering, why is the electronic engine control so important? The EEC calculates thrust with ambient pressure, ambient temperature, and N1 speed. It senses the actual N1 compared to commanded N1 and makes the necessary change in fuel flow. The EEC is also in charge of keeping N2 and fuel flow readings within limits. The EEC may operate in 3 modes: normal mode, soft alternate mode, and hard alternate mode. You may also be wondering, does the exact same engine provide power to all variants of the 737NG? The answer is yes. However, each individual aircraft type, like the 737-600 or 737-800, have specific thrust configurations and a maximum thrust setting that is outlined and configured with an engine identification plug that specifies each thrust rating for each individual variant of the 737NG. Let's refer back to the primary and secondary engine indications we mentioned earlier during this lesson and discuss them a bit more before we move on, as they will be essential for what we discuss afterward. Low pressure shaft speed, or N1, is an indication of the fan rotational RPM speed. It's expressed as a percentage of a maximum RPM. In other words, the power that the engine is producing. The N1 instrument has reference bugs and red lines to display operating limits. N1 is a readout in white color under normal conditions and red color when the N1 operating limit has been exceeded. The EEC computes the maximum rated thrust for the engine during all phases of flight, and it shows as an orange color bug. The active flight phase is shown immediately above both engine N1 instruments. Exhaust gas temperature, or EGT, is an indication of the temperature of the gases that are escaping the turbines into the engine exhaust. It is of prime importance to monitor EGT, just like with N1. The EGT instrument also has a red line that displays the maximum takeoff EGT limit, an orange line that displays the maximum continuous EGT limit, and finally, a lower red line to display the EGT limit during startup. This last line disappears once the engine is started and is stable. Curiously, the EGT gauge also has an engine failure alert that is displayed in amber when the engine is running below its normal idle thrust. and the engine start lever is in the idle position. This alert stays unless the engine recovers or the start lever is moved to the cutoff position. In other words, fuel is isolated from that engine, or unless the engine fire warning switch is pulled. Aside from N1 and EGT, the total air temperature is displayed in degrees above the N1 indicators. Similarly to N1, the high-pressure shaft speed, or N2, is an indication of high-pressure rotational RPM speed. It is expressed as a percentage of a maximum RPM. N2 indicators have a red line to indicate operating limit, and the N2 indications turn red when this operating limit has been exceeded. There are also engine vibration indicators that display current engine vibration levels in white. The instrument has a high vibration limit marked by an amber line. When engine vibration exceeds this limit, the indication color scheme is reversed to draw the pilot's attention. Other secondary engine indications are the oil pressure, oil temperature, and oil quantity. Let's discuss the engine oil system on the 737NG. From small piston-powered aircraft to large turbofan jets, all aircraft use engine oil to lubricate and clean moving parts inside the engine and absorb some of the thermal energy that's released when the engine is running. Engine oil is almost as important as fuel. Without it, engines would overheat because of the intense metal-to-metal contact. The 737NG oil system is divided into three main areas: oil storage, oil distribution, oil indication. The oil storage system is in charge of making sure the oil is continuously supplied to both engines. There's an oil tank in the oil storage system that holds engine oil and allows oil level checks to be done. The engine oil tanks can each hold roughly 20 liters of oil. The oil distribution system is in charge of sending and receiving oil from the internal engine components. When oil is supplied, it's filtered to prevent contamination. After filtering, oil is also sent to the fuel-oil heat exchangers we discussed before, in order to make the oil temperature slightly cooler as it heats the fuel. Similarly to the fuel filtering system, oil also passes through a filter which may end up clogging with contamination. When this occurs, oil bypasses the filter and the oil filter bypass alert appears in the upper display unit. The oil indication system provides cockpit indications that monitor oil temperature, oil pressure, and oil quantity. These appear under the secondary engine indicators. Oil quantity indicators measure usable engine oil and display it as a percentage of the total quantity. When the oil quantity is 18 liters or higher, a full quantity indication is provided in the display units. A low quantity message appears when oil quantity decreases below 4 liters during at least 35 seconds. Also, the related quantity indicator's color inverts to alert the pilots of the oil shortage. Oil pressure indicators obviously measure and display oil pressure in PSI, pounds per square inch. The oil pressure indicators have 3 color bands: white, normal operating range; amber, caution range. Continuous operation in this range should be limited. The amber band is not displayed when N2 speeds are below 65%. Red, operating limit. The oil temperature indicators show engine oil temperature in degrees Celsius. It's measured using 2 sensors at different points that average out the readings and deliver one oil temperature indication. Oil temperature indicators also have color bands that have the same color meanings as the oil pressure indicators. If oil temperature stays in the amber color band for more than 45 minutes, the engine must be shut down, provided all other solutions have not been successful. To sum up, So far, we've had a look at how the CFM56-7B engines on the B737 work, how they are fed fuel, how oil is cycled through them, and what kind of cockpit indications are associated throughout. All of our discussion has assumed that the engines are on and running normally. However, it's time to discuss how someone ignites and starts up these two giant turbofans. Starting up an engine safely, properly, quickly, and efficiently has always proven to be a challenge for most pilots. Even single-engine piston-powered aircraft can sometimes have very tricky startup procedures. It's important to know the reason why special considerations have to be taken in order to achieve safe and good startups, as well as maximize engine life. Us pilots like to constantly simplify things, so instead of going into excessive detail about components, we're going to look at the next few sections in a more procedurally focused way. We'll only be discussing normal startup procedures, as abnormal procedures are comprehensively discussed and evaluated elsewhere in our 737 NGX training. Essentially, there are two different types of normal startups: on ground and in flight. In the previous chapters, we saw that a series of compressors and turbines move shafts inside the engine and that the low-pressure shaft, or N1, turned the engine fan. Now, how do the compressors and turbines move in the first place to achieve this desired fan movement? To do this, there are a couple of engine start switches, one for each engine, that have the following positions: ground, off, continuous, and flight. First, let's assume that everything else needed at this point for engine start is complete. That means that the air system is set up correctly, we have the power needed, fuel needed, and so forth. To get the related engine started, the pilot turns the engine start switch to the ground position. By doing this, the electronic engine control, EEC, and the APU receive engine start signals, and a start valve opens. When this valve opens, a Start Valve Open alert illuminates and power is supplied to the engine starter. The engine starter turns the engine N2 high-pressure shaft through the accessory gearbox we mentioned earlier. The engine starter manages to turn the N2 shaft by converting highly pressurized air into mechanical energy. This high-pressure compressed air is pneumatic power that is usable when the start valve opens. This air is provided by an engine start cart on the ground, an APU, or air pressure from another engine, assuming it's already running. As N2 revolutions per minute increase, all engine instruments must be monitored. However, special attention has to be given to N1, N2, EGT, fuel flow, and oil pressure. When N2 reaches 25% and the N1 has begun rotating, the pilots move the engine start lever from the cutoff position to the idle position. This action opens the fuel spar shutoff valve and allows fuel to start flowing into the engine fuel system towards the fuel nozzles in the combustion chamber of the related engine. Fuel ignition is also started when the start lever is placed in the idle position. If for any reason the engine doesn't seem to reach 25% N2, the engine start lever may still be moved to the idle position provided N2 is at least 20% and the N2 acceleration is lesser than 1% during 5 seconds. This condition is known as maximum motoring. When the engine is started and N2 reaches 56%, the engine start switches automatically move to the off position, and the start valve open light extinguishes. The ignition system supplies sparks to light the fuel in the combustion chambers. There are 2 ignition systems per engine, a right ignition system powered by the AC standby bus, and a left igniter powered by the related AC transfer bus. Only one igniter is necessary in order to perform an engine start, but this redundancy makes the start more efficient. there is an ignition selector switch that may select either ignition L, ignition R, or ignition both. AC buses are comprehensively discussed in the 737NG electric system lesson. From here, normal startup takes care of itself, and the pilots monitor for normal indications. Anything abnormal and quick shutdown can be performed, placing the engine start lever in cutoff and turning the ignition to off. But because we're only discussing a normal start, you'll see a final drop in N2 on the secondary indications. The ignition switch will automatically switch to the off position, which can be heard, and the engine should be running smooth and steady. The normal startup procedure on ground is fairly straightforward. However, as we mentioned before, we will not take into account the possibility of having hot starts, wet starts, and other types of abnormal conditions. The EEC has protection mechanisms where the engine start sequence is either detained or delayed when an abnormal start condition is detected. We've seen how engines are started on ground. Let's have a look at how they're started in flight in case an in-flight shutdown is imminent. Earlier on ground, highly pressurized air provided pneumatic power that was later converted to mechanical energy in order to turn the N2 shaft through the accessory gearbox. This high-pressure air is called bleed air, and we'll be discussing it in detail in the air systems lesson. However, we must know that during a ground start, bleed air is obtained from the APU. When the APU is inoperative, an external power unit may alternatively supply high-pressure compressed air. But those aren't exactly available in the air. The APU would be at times, but not in all cases. There are two types of in-flight starts: windmill start and crossbleed start. In-flight starts may only be performed within a specific altitude and airspeed flight envelope. For the most part, in-flight starts may only be performed at or below 27,000-foot pressure altitude. In a windmill start, the N1 fan behaves like a windmill and spins as the aircraft moves through the air. The 24 fan blades on the 737NG are very aerodynamic. This method does not use bleed pneumatic power, therefore it doesn't use the engine starter. Instead, it takes advantage of the air that is rushed into the windmilling engine to turn the compressors and get the engine restarted. In this case, the engine start switches must be placed in the flight position, where both spark igniters operate continuously. Oil quantity indications may be as low as 0 during a windmilling start because of the lack of compressed air to allow the oil to return easily to the oil tanks. When the aircraft is out of the flight envelope for a windmill start, or when the engine has been shut down for more than 1 hour, a crossbleed start must be performed. This method does use the engine starter, therefore the engine start switch must be placed in the ground position. Neither form of in-flight starting has electronic engine control protection mechanisms. During the rest of the flight, operating the engines is pretty straightforward. For the most part, the autothrust system handles the thrust that each engine produces to match the required flight speed that is programmed into the flight management computers. This, of course, varies according to many weather parameters, company fuel burn policies, and the respective flight phase. When the aircraft is bound to touchdown during the landing phase, the engines are placed into idle thrust. However, there is still some sort of forward pushing moment that the engines generate, which is in the order of 20 to 30% N1. This is not favorable to slow the airplane down to a safe taxi speed. Therefore, the pilots engage the so-called thrust reversers. The thrust reversers essentially change the direction of engine exhaust air to help decrease airspeed after a landing or during a rejected takeoff. Usage of thrust reversers is also beneficial to the gear and brakes, as lesser wheel braking action is required to stop the aircraft in the same distance. Each engine has one thrust reverser with two halves, or sleeves. Reverser sleeves move together with the help of hydraulic power. As the sleeves move aft, a blocker door changes the direction of airflow and produces the reverse thrust. Each reverser sleeve opens to about 45 degrees of the stowed position. Thrust reversers are operated hydraulically. Hydraulic system A pressure operates the engine number 1 thrust reverser, and hydraulic system B pressure operates the engine number 2 thrust reverser. If either hydraulic system fails, the standby hydraulic system powers thrust reverser deployment. When the standby system is used, thrust reverser deployment takes considerably longer time, and asymmetric reverse thrust may be observed. The first sign of asymmetric reverse thrust is an aircraft tendency to yaw and turn into the direction where there is higher reverse thrust. For example, if the right engine reverse thrust system is working normally and the left engine reverse thrust system is working at a lower capacity, the aircraft will tend to yaw and turn towards the right. Under normal conditions, synchronization shafts make sure that both reversers are actuated simultaneously. Thrust reversers are operated with the thrust reverser lever, located immediately forward of the engine normal thrust levers. The reverse thrust levers have to be lifted aft to deploy reverse thrust. The reverse thrust levers have 3 detents. Detent 1, idle reverse thrust. Detent 2, normal operating reverse thrust. Detent 3, maximum reverse thrust. Only 2 detents, maximum and idle, are selectable in your PMDG 737NGX, as opposed to its real-world counterpart that has the normal detent in addition. When the reverser sleeves move from their stowed position, a cockpit amber reverse alert illuminates. When the reverser fully reaches its deployed position, the reverse alert turns green and the reverse thrust lever can be pulled aft of the idle reverse thrust detent. In this condition, normal operating reverse thrust is provided and is sufficiently powerful to bring the aircraft to a stop. When added reverse thrust is needed for short, hot, or wet runways, the reverse thrust lever may be moved fully aft to the maximum reverse position. There is also a reverser light in the aft overhead panel that illuminates when the reverser has been commanded to stow. This light extinguishes roughly 10 seconds after stowage. If the light does not extinguish for 12 seconds or more, a malfunction will have taken place and a master caution will present itself. In either reverse thrust setting, it is not recommended to allow the aircraft to decelerate below 60 knots with the reversers deployed, because of the risk of foreign objects injecting themselves into the engine cowling and damaging components. To provide system protection in the case of thrust reverser uncommanded motion or incomplete stowage, an auto restow system compares actual reverser position versus the commanded position and stows both thrust reversers back to their fully closed position. Shutdown procedures on the 737NG engines are as simple as pulling the engine start lever from the idle to the cutoff position. This will close the fuel spar shutoff valve, de-energize the engine starter, and isolate fuel from the related engine. The engine indicator instruments must be monitored for a normal reduction in all engine parameters. Engines and their components may be a difficult chapter to grasp at first. However, it's essential to achieve a good understanding of their operation, as they are critical to the safe handling of not just the 737, but all aircraft, except gliders. During this lesson, we discussed many things. We saw how engines work, how they are ignited, and how the fuel and oil systems work. Thrust reversers were also discussed. It's fundamental to know that for an airline to start a scheduled service to a specific airport and runway, the aircraft must be able to demonstrate that it will be able to brake satisfactorily without the use of the reverse thrust system, as this is only an extra aid that's available to reduce the landing distance roll and tire wear and tear. We also discussed some of the cockpit indications associated to the engine system. A lot of these will be profoundly discussed during other sections of the 737 NGX training. We only mentioned a few of the engine protection mechanisms and abnormal conditions, especially those related to the EEC and thrust reversers. We encourage you to investigate about abnormal engine conditions and comment on their procedures in the comments section of this video. This lesson covered the following topics: 737 NG Engine System Overview, Engine Fuel System Overview, Engine Oil System, Starting and Ignition Procedures, Thrust Reversers, and a lesson summary. Next, we'll have a lesson on the APU. Until then, throttle on.